Okay, Vandy and Region and Zach, I forgot to record the first part of the lesson. I'm sorry. I was just so excited about the math that we're doing today. I'm sure you are too. So here we are. We went through the first 6 problems. You could check to see if you could generate those. If you can't, that's okay. We'll try. Well, as much as I like you, I'm not going back to help you. So we're just gonna move on. Okay. So let's try 7, 8, 9, 10, 11, 12. Okay. So now, what is different about 7 through 12 compared to the previous ones? Yeah. Now, this is different, okay? These first 6 are what we call recursive. They are recursive because they require the knowledge of the previous term. And so recursive, you always go back to get one to move forward, right? And then back to get one to move forward. You always do that. So it's recursive. Whereas these 6 here are what we call explicit. Not like explicit lyrics on your albums that you buy, but rather explicit, meaning we can find any term. So you don't have to know the first one to find the next one, okay? So they don't give us a first term here, but we would like to generate a sub 1. How do we generate the first term? Look at, we just plug in 1 for n. What's 1 minus 2? 1 plus 1. 2 times negative 1? Negative 2. I don't need to use that negative 2 anymore. Yeah, the rule says if I want to generate a sub 2, I plug in 2 for n, which is 0. Now I plug in 3, and I get 4. Now I plug in 4, 10. Bless you. And I plug in 5. 18. There you are. Now, Larry, remember 10 good things for every 1 negative item. So, did you guys ever play that game growing up that if you say something negative to somebody, you have to say 10 positive things about them to undo that? You didn't ever play that game? We should play that in here. Yeah. All right. Try 8 through 12 and see if you can get 8 through 12 on your own now. These are all explicit, okay? Explicit. Go ahead. I'm going to pause the video now.
Hey guys, he doesn't know I'm doing this. I don't know. What should I say? Is it paused? No, it's going. Oh well. He still hasn't noticed. Oh yeah, guys, I stole the microphone. He's not looking right now. So Emma's about to. Oh, dang it.
Okay, we're back. Here's some answers, which I think everybody got. That's hopefully good. Which one? 12? Which one? No, because it's not recursive. Who did Julia say that? Thank you, Julia. Thank you for putting him in his place. Thank you. Now, I want to show you something interesting, though. You notice this negative 2. When you have a negative that's included to a power, what does that make happen to the sign? The sign changes. Does that make sense? Because you go through odd and even powers, so therefore the negative will either cancel out or it will continue to exist to be there. So let's do this one. We have negative 2 to the 0 power. What's negative 2 to the 0? 1. And then we have negative 2 to the 1 power. Negative 2 to the... Good. That's it. Got him? Any questions on that? Okay, now we're going to get to a challenge. So you have to identify a partner of 2 or 3. So a group of 2 or 3, whoever you want to be by. Okay. So I'll do one example for you, and then you want to see if you can beat your partner to the next one. Now, these are not going to be some, yeah. Okay. So, so for those who didn't see, Solveig was sitting next to Morgan, and Brooke was sitting next to Emma, and now Solveig and Emma are sitting next to each other, and Brooke and Morgan. So who demanded the switch? Brooke demanded the switch. Okay, all right, all right. So Brooke, what does that say about Morgan? Is that what? Are, okay, okay, maybe she'll beat you, but maybe she won't talk smack because that's where Emma and Solveig go. They talk smack. Okay. All right. So I'll do one of the I'll do the second problem for you because the first one's real easy. So what we want to do is we want to write an explicit formula, okay? And so when I write an explicit formula, here's what I do. I write the term above the numbers. So this is my first term, second, third, fourth, and fifth. And what I do when I look at those terms is I try to notice a pattern between the domain and the range. Do you notice something? Squares, very good. Squares multiplied by 0.1, right? If this was 25, we would say, well, that's 5 squared. 4 would be 16. So it's the square of the term number, but then you multiply it by zero point 0.1. So I could write a sub n is equal to zero point 0.1 times n squared. And that would be an explicit formula for that problem. You say that one was an easy one? Uh, I'm gonna let you. I'll let you try 13 on your own against your partners. So you want to race who gets it first? I'll give you a minute and a half. Ready, set, go. Try to do 13. Go. Okay, so some people got it. So again, so Kaylee made a great observation, and she says, "I see it goes up by 8," and she's absolutely correct. It does go up by 8 each time, but so you could write a recursive definition by saying, well, a sub n is equal to the previous term plus 8. But that's recursive. We want explicit. So she's thinking along the right lines to generate a formula. Recursive is just presents some problems later on in mathematics. So we want to write explicit. So look at the numbers. How do we get from 1 to 8, 2 to 16, 3 to 24? We multiply the term number by, and so we represent the term number by using the letter n. So if you want to get the output, you simply multiply the input by 8, and then you get it. That's all there is. Got it? Okay, I'll do another one for you, and then I'm going to let you try one on your own. Let's look at 15. And again, I start by writing 1, 2, 3, 4, 5. So does anybody see? Very good. Good job. Very good. So you can see that if we square the 1, we get 1, add 2, you get 3. Square the 2, you get 4, add 2 to it, and you get, yeah. Hey, I'll show you how to get it. I'll show you how to get it. Watch. This is a trick. I'll show you. What's the difference between 3 and 6? 6 and 11. 11 and 18. 18 and 27. Now, are those constant? they're different each time, right? And because they're different each time, it's not linear. So this is linear. See how these each go up by 8 each time? That's constant. It's linear. So then we go to the second set. What's the difference between 3 and 5? 5 and 7. Is that constant? So since it was a second step, remember you learned this in Algebra 2, that means that it is quadratic. So you know you're going to end up with a square. Race against your partner, number 16. Ready, set, go. You can do it. Stop. Okay. Who got it? Okay, good job to you guys. So if you look, a sub n is equal to, does the top ever change? So you got 3, but on the bottom, look at my terms. 1, 2, 3, 4, 5 is my term number, and my results are 2, 4, 8, 16, 32. Those are all multiples of 2. In fact, they're not just multiples of 2, those are powers of, powers of 2. 2 to the nth. See? 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8, so on and so forth. Question. 17 you can write as recursive. However, there's also an explicit definition for it. Let's do 17 together. What's the difference between, so I'll write, 1, 2, 3, 4, 5, yada, yada, yada. You don't really see a whole lot that changes. But what's the difference between the first two? What's the difference between the next two? 3. So if you see a constant right away, then is it first degree or second degree or third degree? It's first degree. So I could start by this. A sub n is equal to 3n. But we have to adjust it a little bit. We all know that if you have something that's first degree, you can always add or subtract a constant onto the end, right? So if I take 3 times 1, what do I get? 3. I don't get -2. So what would I have to subtract to get -2? -5. Let's see if that works for the others. 3 times 2 is 6. -5 is, works for the second one. Let's try next. 3 times 3 is 9. -5 is, and so that continues to work for them all. So I knew the 3n because my difference was 3. And you guys, I will show you ways to figure these out mechanically tomorrow. I just want you to try to guess at a few. So you want to try the last one? All right. So when I look at this one, I like to write them as fractions instead. So watch how I do this. So my first term is 5, right? Over 1. My second term is 1 over 1. My third term, what is 0.2 as a fraction? 1 over, what's my fourth term? What is 4/100ths? 1 over 25. Oh, what's happening every time? So we're multiplying by 1/5 every time, aren't we? So that's going to be, well, we had to play with it a little bit. So watch what happens here. What's 1/5 to the 0 power, or to the first power? 1/5 times 5. 1. Does that give us 5? No, it doesn't. Okay, well, I'm just. So instead of multiplying by 5, what can we multiply by? Close. 25. Let's try that. What's 1/5 to the 1 power? Times 25? 5. So we got it. And you can even clean it up from here a little bit. You can, use the the 25 and the 1 over 5 in certain ways and change the exponent. But I won't go through all that. But I just want to show you that there are ways we can model it explicitly. So, any questions? Okay, flip it over. I won't have you do any homework today, but I want to try to get, I don't want to spend too much time on this stuff. But now we have something called summation notation, okay? And this is really, really cool. You don't have to write this down, but the Greeks used a way to summarize their findings. I'm sorry, not just the Greeks. It's just a Greek letter. We use this thing right here. So if you want to write this down somewhere where you have room, that's fine. That's the capital letter for S in Greek. Small letter is like that if you're in the middle of a word. If you're at the end of a word, then you write that. But that's a capital letter for S in Greek. And in mathematics, we mean the sum. It means the sum. Everything added up. You maybe have seen this on like Microsoft Excel. Like you see that button, you press it, adds up the whole row. And so what we do here is we identify where we begin. And then we also identify the end. And then we also identify the rule. So sequences and series, they take up a lot of space. A sequence is just a set of numbers. A series is a sum. A series is a sum. And what we want to do is we want to express it in a more kind of concise manner. So this is really cool. Like when you do this, and you could take it home, or you could show your parents what you're doing. Be like, "Wow, you must be really smart. I don't understand anything you're doing because you're using this weird symbol." Did you take Greek when you were in high school? Okay, so let's try one. It says, write each series in summation notation. First of all, can you identify the rule? It goes to +2, +4, or is that a -2? So it jumps back and forth between positive and negative. -2 to the n power is the rule. So I write my summation. Okay. I have a -2 to the n power. What is my first term? -2. Okay. And so I'm going to call that, I'm going to start with n equals 1. How many terms do I have? 5 terms. So if I saw this written down, I could expand it to look like this. This is expanded form. This is summation notation. Expanded form, summation notation. So we make it smaller. Now you're like, well, big deal. It's 5 terms. Well, yeah, but what if it's 140? What are you going to do? You're going to write it all out? No, you want to write it like that. Okay? So that's where we'll pick up tomorrow. We're going to expand those type of things. We're going to actually see what they add up to. Some of these we can actually find what they add up to. And so, cool beans. No homework today.